you for coming. I'm sure you gave up a lot of good food and everything to be here, because you all could have been at home, right? Your parents would be cooking you things. Unless your parents don't live around here, in which case I'm the only family you have, and you should just be thankful that I have the conscience to come in. All right. So, hey, come over here. Come here. Just for all you fans around the world, Trinidad and Tobago, yeah, South Korea. This is my son Alex. He came in to watch today. You say hi? Very good. Okay, you go right. All right, so we've done curve sketching this week, and I figured we'd just do another example of it, because it basically covers most of the material from the class, so it's like a total review of the course. So, all right, so we start with a function, and let's make it easy. The reciprocal of a cubic. And, well, it might be useful when we're doing our computations to also have it written out in full. Especially when we want to take derivatives.
I'm back. I'm back.
Okay, you gonna take notes?
Huh?
Take some notes. Copy down what Daddy's writing. Okay, so what do we got? Well, let's see. Guy said first a critical test, then a cavity. Right. So we can either write in our then a second test, or we can write in it's a sign. Okay, so let's just do it's a sign. Okay, so let's start at the beginning. Let's check out the domain. So what is the domain of this function? Well, where do we get problems?
-3.
-3 is going to be a problem. Where else might we get a problem?
0.
Yeah, I'll copy with you.
Okay. So the domain will be all real numbers except, well, I'll write it in numerical order, -3 and 0. Very good. Okay, so already we're thinking, right, we're getting zeros in the denominator at 0 and -3. So that's a very good chance that's where our vertical asymptotes are going to be. Okay, so keep that in mind. Then come the intercepts. And we always check the x-intercept first. Okay. So the x-intercept is where the function equals 0. The function is a fraction. And the fraction equals 0 when the numerator equals 0, right? When the top equals 0. And the top is a constant function 1. So this function can never be 0. So there's no x-intercept. What about the y-intercept? The y-intercept is when we let x equal 0. Okay? But we're not allowed to let x equal 0. Okay? Because 0 is not in the domain. So there's no y-intercept either. Okay, so interesting. We get no x or y-intercepts. Okay, next comes symmetry. Again, okay, let's take a look at it. You have a fraction that's 1 on top, so that's an even function. And on bottom you have x squared, that's an even function. But then you have x plus 3. That's no good, right? You have an odd function plus an even function. And remember what happens when you add odd and even, you're just hosed. So you're not going to get any symmetry from this. Oh my goodness, look at that. We've gone through 3 things and we hardly have any information. Right? We just know there's a couple possible vertical asymptotes. All right, well, let's check these asymptotes. Okay, well, as long as we know that 0 and -3 are the places to check, okay, let's check them. Let's look at the limit as x goes to 0 All right, and we should always check both sides of our function. Okay, so we'll check it as it goes to 0 from the left, and we'll check it as it goes from 0 on the right. Okay, so if I put negative numbers in, right, numbers smaller than 0, okay, this x squared is positive, no matter what I put in. And x plus 3, well, with numbers less than 0, but close to 0, what is this term going to be, positive or negative? It would be positive, right? It's close to 3. Okay, so you're getting positive and positive and positive, so everything's positive. Okay, so if it goes off to infinity, it's going to go to positive infinity, not minus infinity. And let's see, as it goes to 0, sure enough, right, the bottom is going to 0 times 3, which is 0. So it's going off to 1 over 0, which means it's going off to infinity. Okay. And coming from the right side, well, none of that changes. Okay, this is still positive. That's always positive. Okay. So it's going off to infinity in both the left and the right. Okay. So we're going to get a vertical asymptote on both sides of 0, and they're both going to go up to infinity. Okay. What about minus 3? We check it from the left and the right. Okay. Well, now let's see. Okay, the square is always positive. Don't have to worry about that. Now over here, as you come from the left, you have a number slightly smaller than minus 3. So it's like minus 3.1. Okay. So what is that going to mean when you add it to plus 3? You're going to get a negative number. Okay. So this is going to go off to minus infinity. And as you come from the right, well, now you have a number like negative 2.9. And when you add it to 3, you get a positive number. So the whole thing will be positive. So it goes off to positive infinity. Okay, so here we have a vertical asymptote on both sides of negative 3, but on the left side it goes down to minus infinity, and on the right side it goes up to positive infinity. Okay. So let's start our graph. And the two key points that we found so far are 0 right, and minus 3. And we know at minus 3 we're going to get a vertical asymptote. And at 0 we're going to get a vertical asymptote. Okay. And on the left side of 3, it was going to go down to minus infinity. And on the right side it goes up to positive infinity. And around 0 it goes to infinity on both sides. Okay. Now let's check the horizontal asymptotes. Okay, so the horizontal asymptotes is when we take the limit as x goes to plus or minus infinity. Okay, so well, as x goes to minus infinity, let's see, well, the x squared is always positive, right? And so it's just going to positive infinity. And this down here is going to negative infinity. So what's the product going to? Negative infinity on the bottom, right? Which means the whole thing is going to 1, so it's a 1 over something going to negative infinity. 0, right? The negative doesn't matter. Okay? Other than the fact that we know it's negative down there, but we don't even need that. And if we went to positive infinity, well, the same thing has to happen, because if it's going to 0 from one direction, right, then the odds are pretty good it's got to be going 0 in the other direction, given the way this function was designed. But let's check. All right, as x goes to infinity, this goes to infinity, this goes to infinity, the whole thing goes to something which is 1 over something going to infinity, so it also goes to 0. So we have both a left and a right horizontal asymptote, and they're both 0. So it's going to approach 0 as we go. You right there. Okay, so what's next? So we have our asymptotes. Where are we at? ID test. Okay, so we need to take a derivative. So the derivative of our function, well, we could use the quotient rule, or we could just notice this is 1 over something. So it's really just the bottom term to the minus 1. So this will be, if you like, if you raise this to the, think of this as x cubed plus 3x squared to the minus 1, then the derivative will be minus x cubed plus 3x squared to the minus 2. Am I done? No, I have to do the inside, right? So times 3x squared plus 6x. Which, if I want to rewrite it as a fraction again, becomes negative 3x squared plus 6x divided by x cubed plus 3x squared. Or if I factor, okay, I can factor out a 3x, and I get x plus 2. And on the bottom, well, I already know how this factors. It's x squared times x plus 3, and I just square it. Hey, how's it going? But now I have to square everything, so it becomes x to the 4th times x plus 3 squared. Just take this bit here and I square it each term. It's a nice R. Okay, so now what are we interested in? Well, we're interested in the critical numbers, right? And the critical numbers are where the derivative is 0, right? Or where the derivative is not defined, but the original function was defined. So let's take a look here. What are the critical numbers of f? Well, critical numbers of f first is where the derivative is 0. So where am I going to be 0? Well, we have to be careful. Yeah. All right? You might think, well, we have these x's, we could cancel, right? Well, what does it mean to cancel? It really means we have to divide by it. Yeah? Top and bottom. And if x is equal to 0, you can't divide by it. So we can't just cancel, right? Unless we make sure we're saying x is not 0. Okay, now, if I put a 0 in here, then I also have a 0 in the denominator, which means this function isn't even defined. Okay, so normally we say, okay, where is the fraction 0? Well, when the numerator is 0. Okay, but you always have to be careful. Make sure that if you plug in something into the top that gives you 0, you don't also make the denominator 0. Okay, so 0 is not one of the critical numbers. It's not even in the domain of the function. Okay, so then the other place you can get a 0 is a minus 2. Okay, and that's an honest-to-goodness critical number. All right. Now on the bottom, you can check and see things where the derivative isn't defined. It's not defined at 0, but that was already thrown out. It's not defined.
That do me.
Do you?
What's something?
Oh, okay. It's not defined at minus 3, but that was also thrown out. So that's it. These are all the critical numbers. That's the only place you can have a local max or a local min. So we know minus 2 is not going to be an important point.
Can you do me?
What should I draw you?
B.
A B?
B.
Okay, let's do a B. There you go. Okay, so now let's just determine what it is, right? Okay, so how do we do this? Well, we'll do it, say, with the sign graph, and we can use the ID test. Okay, and the first derivative test. Okay, so let's, at this point, draw our sign graphs down. Okay, so for f, the interesting places, okay, is where f was 0, which it never is, or possibly these vertical asymptotes, so 0 and minus 3. And for f prime, we just saw that the interesting points, well, there's minus 2. And then we also, we've seen that it usually is nice to take a look at these other points, which aren't really critical points, right? 0 and minus 3, but are somehow relevant to things anyway. Just good to know where everything's going. Oh, you have a frisbee. Very nice. Okay, so first, for the original function, when we do the sign graph, if you throw in a really big negative number, right, then we saw, okay, that goes to positive and that goes to negative. So this whole bottom goes to negative, and the whole fraction then is negative. Okay, now the minus 3 came from a linear term, so the sign is going to switch. And this matches what we thought would happen, right? On the left side of minus 3, you went to minus infinity, and on the right, you went to positive infinity. It should be positive on that side. And then you go to 0, and 0 comes from a square term, so it's not going to switch direction or sign. Which again matches what we knew, right? For the vertical asymptote, we knew it was going to go to plus infinity on both sides. Okay, so now we'll do the sign graph for f prime. Okay, so let's see. If we throw in something really negative into f prime, what do we get? All right. So the whole thing is negative. Now what's on the inside? So I put in a big negative number. Negative times negative is positive. That's positive, and that's a square, so that's positive. So everything is positive, and then negative on the outside, so we get negative. Okay. And now minus 3 came from a square term, so it's not going to switch signs. Okay, that's good. Okay, where did minus 2 come from? Well, that came from a linear term, so that will switch signs. And where does 0 come from? Well, 0 actually comes from 2 different places. Right? It comes from an x and an x to the 4th. So what do you think will happen? Will it switch signs or not switch signs?
I don't think it will.
You think it will?
No.
You don't think it will? I did catch it. Well, think about asymptotes. Right? The asymptote at 0.
Actually, in that case, yeah, well.
Yeah, all right. Okay, so you're coming in from the left side is going up. Now, when you come in on the right, well, the graph makes it look like it's going up. And remember, we always read left or right. And left or right is going down. So it must switch signs. Right? Another way you can think about it is, well, if you could cancel these, you'd have an x cubed on the bottom. And that's an odd power, so it should switch. Okay, so this tells us, right, that at minus 2, we get a local something. Okay, well, let's see, it's negative and then positive, so it's a local minimum. So let's actually compute it. F of minus 2. See what that minimum is. Well, if we put a minus 2 in, minus 2 plus 3 is 1. And then times 4 is 4. So f of minus 2 is 4. So that's our point. So 1, 2, 3, 4. Okay. And that's going to be a minimum. So it's going to go up. Okay. One moment. Hey, Alex, come here. Don't you ever do that again! Hey, Alex. Why don't you sit down with the person? Oh, Okay, so we have a local min.
I'm right here. I'm in right here.
Okay. So the only thing we don't know, right? We've actually had pretty much everything about this graph. The only thing we don't know is the concavity. Hey, look, you just hit Shannon. I think Shannon's going to cry now. Oh no. You say, I'm sorry. Lo siento. Okay, so we've used our first derivative test. Now we're just going to check the concavity. So we need to take a second derivative. Okay, so it's very scary to take the second derivative now. Okay, what we need to do. Okay, now, as long as we accept the fact that this function is not defined at 0 and the derivative is not defined at 0 and the second derivative is not going to be defined at 0. We can cancel. Okay. So when we cancel, right, and of course we're already adding.
Can you wipe this off? Can you wipe this?
Oh, how about you just go to the next page? Watch this. Okay. Go right on the page. Here, go sit down. So as long as we're away from 0, I can do this division. Right? No problem. So that should simplify things just a tad. Not much, but just a tad. Okay, so I have to use quotient rule. Okay, so I do low x cubed times x plus 3 squared. D high. Okay, well now it's helpful because now I just have 3 times x plus 2. And what's the derivative of 3x? 3 times x plus 2. 3.
I get 1.
Derivative of x plus 2 is 1. So
Hey, I get 1.
okay, you get 1. Okay, so I move a 3 out front. Okay, minus, now I do high, 3x plus 2, times the derivative of the low. All right, well now, I got to do it. I got to use the product.
They do 1. They do 1.
A 1, like that?
Oh.
Okay, so let's see. I can hold the x cubed and then multiply by the derivative of x plus 3 squared, which I use the chain rule, right? 2 times x plus 3 to the first times the derivative of x plus 3, which is 1. Okay, so it's just 2x plus 3. I'll put the 2 in front. All right, x plus 3.
They
Plus,
do 1.
now I hold the x plus 3 squared and take the derivative of x cubed, which is 3x squared. So 3x squared times x plus 3. And then all of this over the square of the bottom, which that at least is easy. X to the 6th times x plus 3 to the 4th. You know, I used to bring him to class when he was a little baby. I'd wear him on my chest in one of these baby Bjorns. And I would teach. And at the end, he would have all this chalk dust on his head. Do you remember that?
Uh-huh.
Yeah. Okay, now we must be able to factor some things. Let's see. I have...
I'm not draw a B. I'm draw.
Okay, you do a B. I have 3 squared and x plus 3. Okay, so just 1x plus 3 and x plus 3. So I can get rid of an x plus 3. And there's a 3. So 3, and then there's an x cubed, and an x cubed and x squared. Okay, so I can pull out an x squared and an x plus 3. And then I'm left with an x. Thank you. Times x plus 3 minus, okay, I have an x plus 2 times, okay, I'm left with a 2. I pulled out an x squared, so I just have an x. I pulled out the x plus 3 plus, I still have a 3 in there. I pulled out the x squared, so that's gone, and I pulled out 1x plus 3, so I just have x plus 3. X to the 6. So I think we can simplify a little bit from here.
I missed the B.
You missed it?
Uh-huh.
I hope it doesn't sting you.
Can you draw space for me?
Space?
For me.
Well, here, go right on the sideboard.
No, that's it. I use this one.
All right, so let's see. I can copy the first bit, 3x squared times x plus 3. And let's see what's on the inside. So, well, I'm going to have to expand all this out, and then it should cancel a little bit. Okay, I have an x squared plus 3x. And then, well, let's see. On the inside, this bit, I have 2x plus 3x is 5x. And then I have plus 9. So x plus 2 times 5x plus 9. So I get a minus 5x squared. And let's see, 9x and 10x is 19x, so minus 19x.
Daddy.
And then plus 18, so that becomes minus 18. Did I leave out anything? Okay. So 3x squared, x plus 3. Okay, so I have x squared and minus 5x squared is minus 4x squared. And then I have 3x and minus 19x is minus 15x. And then that's it, just minus 18. Over x to the 6 times x plus 3 to the 4th. And is that factor? Well, I can pull a 2 out if I want. It makes things easier. I just put the 2 into here. And I can make it a minus 6, and then all these become plus. Okay, does that doesn't look like it factors nicely, does it?
I get R.
You can cancel
2 times, oh no, actually it will factor. It'll go as 2x plus 3 times
Daddy.
x plus 3, because you get 2x
Daddy.
squared,
Daddy.
6x,
Daddy.
oh, that's 3x.
Daddy.
Yeah. What's up?
I get R.
You got an R?
Uh-huh.
Oh, wait, what about... No,
R.
that one.
R. I get R.
Okay.
Draw me R.
Okay, here's an R.
Daddy, talk about the R boost.
Okay, so we're kind of stuck on that one. All right, but remember, all we ever want to do is get the sign graph. Okay, so this is probably enough, because it's a quadratic. We can use the quadratic formula, even if we can't factor it. Okay, so where is this thing 0? So the derivative of 0 implies x is, well, okay, well, we're not allowed to choose x equals 0 for the same reason as before. Minus 3, again, is going to be a problem. So we don't need to worry about that point. So the only places we're going to get anything is coming from this quadratic. So x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. You know that song?
No.
No. Okay, minus 8 plus or minus the square root 64 minus 4ac, so 18 times 4, which is 72. Look at that. Doesn't even matter what's over, but it's over 4. Right? You have a negative under the radical, which means there are no roots. Okay? Which means our sign graph is going to be very easy. Right? It means whatever we put into this thing, we should always get something positive.
Hey, Dad,
Sorry, but we should always get the same sign out, rather.
R4.
Yeah.
R4.
R4. Like Darfur?
No,
But something seems wrong about that to me. Right? And why does it seem wrong? Well, that's certainly going to be... Oh no, actually that's not that bad actually. I forgot about that -6 in the front. Now it seems worse. Okay, all these terms with the square on them, those are all going to be positive. Yeah, eventually. Well, I mean, the ones, just these ones with strength and power, those are positive. Hi.
Yes. R14.
Oh, very good. R14. Very nice. Actually, if you get rid of this, it's R for gamma. It's a Greek letter. Okay. If we put in a big negative number, what happens? Well, this dominates. So that stays positive, that's positive, positive, positive. And that would become negative. Times that would be negative. So the whole thing would be positive. But if we put in a really big positive number, then all these are positive, and then that would give you a negative. So there must be somewhere where it's switching. Where is it switching over? Well, notice here, if you put in a -3, I mean, everything else here, you know, looks fairly positive. Okay.
Dad, there's RTB.
Oh, this is never 0, which means at some point it's positive, and if it's never 0, this is actually a corollary of the intermediate value theorem. If something is positive and never hits 0, can it ever be negative? No, right? So since this function is positive somewhere, and we know there are no zeros, it must always be positive. So everything here is positive except for that term and then that little negative out front. So everything is determined by here, right, by these things. Okay. So as you go to something bigger than -3, this is positive. Something less than -3, this is negative. Okay. So this is where I was telling you it's a good idea to test these points which aren't really critical points, don't really count, they're not zeros. You put them in anyway because things can happen. So let's just put everything in that could be a problem. So -3, 0, well, that's about it. Those are the only real problems. We know now that if we put in something to the left of -3, that we're going to get positive, and to the right we're going to get negative. And on the right of 0, well, everything, all right, these are already positive, so the 0 doesn't really change anything. So it can't change. But you can plug in big numbers if you want to. Okay, so now we know the concavity. And now we know everything we need to graph it. Okay, so let's take a look. On the, what happened? Oh yeah, there was the picture, right? So on the right side, or the left side of -3 goes to -infinity. And it is positive concavity, so it's actually concave up. Okay? So it's not going down like this. Right. It's actually going down. It's got to do that thing where it goes down like that. That weird, shouldn't go that way concavity, right? Yeah. Okay. On the other hand, we also know, let's erase this for a second. We need to make some room here. We also know we have a horizontal asymptote that it's got to approach. Okay? Can it cross a horizontal asymptote? Well, in general, can you cross a horizontal asymptote? Yes. Absolutely. But in this case, you can't because there are no x-intercepts. Right? If it crosses the horizontal asymptote, which is 0, it would have to be an x-intercept. Okay. So it's got to come up. It can't do the nice thing like that. It's got to go the other way. It's got to be... Boy, I don't even know how to draw that. No, it's got to stay positive. I have no idea how to draw a positive concavity going in both directions to an asymptote. So it's got to definitely... No, I've changed asymptote. How do you do that? Anybody have any idea how to draw that? No idea. Let's save that for later. See, watch here. We'll put in two sides to it. We'll go, no, can't do like that. It's got a...
Make a smiley face.
A smiley face. Ah, there you go.
Think smiling.
Except go the other way somehow. All right, let's see. On this side, maybe it's easy. Everything is, oh, brother, negative concavity? I feel like we must have made a sign mistake, don't you?
Yeah.
Did you see where I made a sign mistake?
No.
Because it would be okay if everything was switched. So let's just quickly see. If you ever have a problem graphing, it's
Oh, check.
I see our sign mistake. Oh, it's so obvious. Look, when we did the derivative, we got a negative.
Oh, the cancel.
And we didn't actually do, when we did at the end of the day, we didn't, look, when we started taking the second derivative, we didn't factor in that minus. Okay, the nice thing is we can just throw minuses everywhere. Phew!
Oh boy.
Okay, good. So now we just change all the minuses to pluses and pluses to minuses. This is why yesterday I made that comment. The one thing we can guarantee is that we made a mistake. Okay, so now it should be much easier to draw this. So it should be concave down in both directions. So going up towards the asymptote, going down towards the vertical asymptote. And then on the other side, it's concave up the whole way. Okay, it's got to go down and hit the minimum, turn around, and go up to the asymptote. And then on the other side, okay, it's again still concave up, and it's got to go down to the horizontal asymptote. And again, it can't cross the asymptote because there's no accent.
Hey, don't draw now. Put that back. I'm not draw.
Well, it's okay, Alex, because look, we finished. We graphed it.
You finished it?
I did.
Okay. This one more. Here. Sit right here.
Sit right there.
Uh-huh.
Okay.
Hey.
Yeah.
What about R and a B and a C?
R, B, and
Can I do that?
Maybe I should record this?
yeah, let's camera.
I don't know if I get those kind of angles.
Oh, we have the graphing
Sit
calculator?
right here.
Graph it
Guys,
for us.
sit right here.
Oh, I'm videotaping you. You wave to the camera? Oh, here, do it again. Do it again. Hi. Hey, Alex. Say yabba dabba da.
Can you hold on to this?
Sure.
Color.
Okay. So any questions?
Dang,
And any of them will start with, how can you always make errors when you do this? And how can I avoid them? The answer, I know why I make errors. I don't know how to stop them. So is it clear how once you get all the data, you can put the graph together? Yeah.
So if we do an error on the final like that, like, is it gonna like?
So this is exactly why you want to write out all your steps. Because if you write out all your steps, and I can see that your method is correct, but that you make some silly error, like I did, leaving out a minus sign, I'm not going to penalize you, you know, if I do it won't be much, you know. What should we write down?
Don't wipe this off.
Oh, wipe it off? Erase it?
Uh-huh.
So one nice thing though is,
Hey, Dad, you did.
because I'm going to have one of these on there, I know that it's going to take a long time for you. So I can't write a very long test. You know, I was thinking, what I did, I looked at the, by the way, did you graph it?
Yeah, it doesn't look anything like that.
Dad,
Where did we mess up?
But,
Are you sure it's our fault, not the calculator's fault?
yeah, I put a lot of brackets on.
Now what can you graph it?
The minimum's at 0.
Minimum 0?
Well,
Let's see. Okay, well the right side we have correct.
yeah, this is fine.
And the left side, we're okay. It doesn't, yeah, it's not happy about a vertical asymptote. But it thinks the minimum is at, what's that point? -2. Can you zoom in on that minimum
Oh,
point?
yeah, sure. Looks like it's -2 and y is 1/4.
1/4. Okay, well let's check. Maybe we just computed this. Maybe maybe I was being stupid.
Oh yeah.
And I put in, right, look, I put in 4, or
Yeah.
-4, and I didn't do 1 over it. Isn't that right? Or it should be -2. Okay, so that's 1 times 4 is 4, so it should be 1/4. Okay,
Yeah.
we put 4, and it should be 1/4. Okay. So, like I said, we will always make a mistake. Okay, so there's 1/4. Okay, but now at least we knew the picture was generally correct, just specifically wrong. Okay, so now this is better. Okay, well, I was really worried when you said it wasn't even close. I was really worried.
It didn't look close.
Okay, if you'll notice on your calculator, they don't do vertical asymptotes very well.
Yeah.
And there's actually a few functions that you can throw into just about any calculator, and it will graph them incorrect, which is kind of strange.
Yeah.
Even the really solid programs like Mathematica, they'll miss half the graph. Right? Things like, I think x cubed is one of them that they just don't do well. It's either x cubed or the cube root of x. They just totally, you cannot handle that. You do the whole thing. You write it in a completely different form to get it to graph it correct.